So last time we introduced the idea of imaginary time Green's function. The purpose of introducing such a counterintuitive quantity is that we are able to combine the thermal factor e to the minus beta h and the unitary evolution operator u of I in the interaction picture so that you could further simplify this Green's function calculations. And so let me just repeat the procedure. So this G italic is the imaginary time Green's function. It's defined as this minus sign of this time ordered operator psi dagger with the different imaginary time tau and tau prime. And depending on what, whether this tau and tau prime, which one is bigger, we have two different forms as we introduced earlier for the real-time Green's function. So if tau is larger than tau prime, and we get an overall minus sign here for both bosons and fermions. So you put this psi to the left of the psi dagger. But if tau is less than tau prime, we need to switch the order between psi and psi dagger. And depending on whether our particles are bosons or fermions, for bosons we get a minus sign, for fermions plus sign. So let's just start from this tau larger than tau prime. In such a case, you simply just look at this first expression here, and as we already mentioned last time, that the partition function, or this Boltzmann weight, is actually decomposed in terms of e to the minus beta h0 times ui beta 0, where ui beta 0 is nothing but this time order exponential operator, which depends only on this potential term. Remember that. Okay? So let me just repeat this ui tau prime time order exponential. Good. So remember now this inverse temperature beta, which is 1 over kBT, in this formulation is understood in terms of imaginary time, right? So this ui beta 0 refers to the fact that you get integration of this v potential term from imaginary time 0 to imaginary time beta. So later we will make such connection between this imaginary time and the thermal factor 1 over kBT. Good. So this is a very good indication that somehow the thermodynamics is actually linked to the dynamics. So the time correlation is actually connected to the thermodynamics. So this is the most tricky part of this many-body quantum theory in terms of this Green's function. So the dynamics which governs the time correlation of your quantum particles is actually tied to the thermodynamics. So now you can see that the beta plays the same role as imaginary time here, because you can combine all this unitary operator ui from this thermal factor and also from this time correlation. So you can use this unitarity property of this ui operator to actually rearrange all these ui factors. You could use these properties tau 1, tau 2, ui, tau 2, tau 3, and so on. So this is the same as trace of ui, tau 2, tau 3, ui, tau 1, tau 2. And you have this properties, nice properties of this ui, such that this tau 1, tau 2, tau 2, tau 3 is actually ui, tau 1, tau 3. So we will prove derive those relations later, but this is just the nice properties of this unitary operator ui. So now you could just use those nice properties to simplify all those ui factors right here inside the trace, and then at the end of the day you'll get simply just ui beta 0, because all the other ui's are cancelled. Ui 0 tau, tau prime, and tau prime 0, you get ui 0 0. So if you rearrange all these ui's inside the trace, you are freely move those ui factors around so that these three factors just cancelled. You get unit matrix, and you left only with the ui beta 0. So this is the highly non-trivial step, but this is the power of this using this imaginary time representation for the Green's function, also interacting picture. So now for tau larger than tau prime, this Green's function G italic tau prime is given by this looks horrible, but already simplified expression right here. So later we will do Taylor expansion or some kind of a perturbed expansion about this UI factor in terms of this powers of this potential term as a weak perturbation term, that this could actually expand this trace term in terms of the powers of this V, and then we could just apply this Feynman's rules and Feynman diagrams to simplify this Green's function. So we could decompose these complicated correlations functions in terms of non-perturbed Green's functions. So this is for tau larger than tau prime. For tau smaller than tau prime, you get almost the same factor, except now you get a minus plus sign in front, because now you need to switch the order between this psi and psi dagger. But other than that, you get almost the same. So combining these two limits, you get this general expression for this imaginary time Green's function, which says that you need to divide the trace by this partition function z, but the partition function is given by the trace of this e to the minus beta h0 times the ui beta 0, as we already mentioned last time. So, but you have this e to the minus beta h0, which has nothing to do with all the other terms, so that this numerator has a factor e to the minus beta h0 cancel exactly by the same factor in the denominator. So you get this cancellation of this e to the minus beta h0. And this is the final expression, which looks really clean, which says that the only thing that you need to do is to calculate this trace. And then you divide this trace by this expression value of the ui operator, sandwiched between 0 and beta, and that's all. So this Green's function in the imaginary time domain becomes calculable and durable. So before introducing this imaginary time correlation functions, it is impossible to really calculate the Green's function, capital G, t, and t prime, which has this, remember, this u, t, t prime, and so on and so forth. So if we don't introduce this imaginary time, there's no way that you could actually combine this thermal factor and this time evolution operator, because one factor is, contains the real exponents minus beta h. The other ui is actually e to the I integral over dt v t bar from t. So carries imaginary in exponent, so you cannot combine these two exponential factors. One with the real exponent, the other is purely imaginary exponents. That's not possible. But once you define this imaginary time correlations, and this t is replaced by I tau or tau, then this tau becomes real. And then you could actually combine and simplify the thermal factor and this imaginary time correlation function. Okay, so this is the trick, and we will go back to this many, many times later, but this is setting up the stage for you to understand why we need to introduce the imaginary time correlation function. So any questions so far? So do not worry about this kind of UI, evolution operator. You will see that very soon. So let's take a short break. When we come back, I will describe the periodicity of a temperature or thermal Green's function, imaginary time Green's function. And from this periodic properties of the Green's function, we could derive so-called this Matsubara frequency, which is kind of an imaginary frequencies when we Fourier transform this Green's function to frequency domain. So let's take a short break. So you could read the corresponding chapters in Flensburg and also in Fetterwachka, also Nagler and Oland. So these formulations are everywhere. So it's easy to find them out, but it's not so easy to understand. Yeah, so this is, I think, the trickiest part of this many-body theory. Once you really overcome such a tricky thing or detour, and you understand much better this temperature Green's function. Suppose we consider this thermal or temperature Green's function defined in an imaginary time domain, and we restrict the interval of this tau and tau prime to be between 0 and beta. Remember, beta now becomes the upper limit for imaginary time. So you will find very interesting, nice properties of this thermal Green's functions within this window of 0 and beta, and consider tau prime positive, and we have this definition. As I mentioned already, this is minus tau is larger than tau prime, minus plus tau is less than tau prime. So let's just look at this quantity here, and let's just plug in this definition, which is minus plus, because now tau prime is positive, which means that tau is actually less than tau prime, and tau is 0. Since all the Green's functions depends only on the difference between the coordinates, say x minus x prime or tau minus tau prime, so sometimes it's easier to simply just set one of the tau to be 0. So for example, here I set tau equals 0, and tau prime is actually tau prime minus tau, if you wish. So if tau prime is positive, which means that tau is less than tau prime, which means that you need to adapt this definition, which is x0. So let's just plug in this definition of this thermal averaging here, and which is e to the beta chemical potential capital omega, and trace. So z is actually this, and k. So if we consider the ground canonical ensemble, and you need to include this chemical potential term, so the Hamiltonian is actually shifted by minus mu times n, where n is number of your particle. So you can show that this is really the same thing, because this is, so based on the cyclic properties of this operators inside the trace, you could very easily rotate the ordering of those operators, and they are the same, B, C, A, and so on. The trace ABC is the same as trace CAB, and it's the same as trace BCA. So you could use this nice properties of this stuff inside the trace, and then you can show that this is given by this first line here. Okay, and also you can verify that given by this. To see this from the first line to the third line, we have used the following identity here. Okay, so I can just rewrite this psi alpha x0 times e to the minus beta k. It's the first two vectors right here. I can simply rewrite this in terms of this expression, where I simply just multiply the whole thing by e to the minus beta k times e to the beta k, where these two factors simply cancel to get unit, but you will find this is useful identity here. So the power of this insertion of this identity is that you could combine these three operators over here, and by definition, this is nothing but this Heisenberg operator at x and beta, because this is nothing but this imaginary time evolution of your Heisenberg operator. Remember your Heisenberg operator, Schrödinger. So in the usual definition of this Heisenberg operator in the real time domain, and it is the time evolution of the Schrödinger operator, right? So you simply just perform such unitary transformations, taking you from the Schrödinger operator at time equals 0 to the Heisenberg operator at time t. So now you simply just use the imaginary time to define such a transformation, and you could simply just call this psi alpha x beta. So the beta refers to the imaginary time right here, because this plays the same role as it over here. And that's how you get this line over here in the middle. Sounds like magic, but you will get used to such magic. So let's just continue. So once I derive such a identity here, so I can simply just use definition of this Green's function, which is nothing but plus minus g alpha beta x prime tau prime, where I use the definition g alpha beta x prime tau prime is given by minus the thing. Okay, so by definition, this g alpha beta x prime tau prime is given by this expression here. Since tau and tau prime are within this range of 0 and beta, so beta is the largest imaginary time you could have in this problem, so that tau prime is actually less than beta. So beta is larger than tau prime, so then we could simply just use this definition right here. And therefore, there's an actual minus sign right here. So you could simply just, using that relation, and multiply this by actual minus sign. And then you could just relate this Green's function at two different imaginary time. So the original Green's function is g alpha beta x0 x prime tau prime. But the final Green's function is this plus minus g alpha beta x prime tau prime. So you simply just relate these two. So this is a very useful relation of this imaginary time Green's functions, which says that you could simply just shift your initial imaginary time from 0 to beta, and when you do that shift, remember you need to multiply the whole thing by plus minus sign, and that's it. So this is true when tau prime is positive, namely tau is less than tau prime, and you can show that this relation holds for the other way around. And similarly, when tau is positive or tau larger than tau prime, you get the same relation. So let me just write it down here. You get g alpha beta x tau x prime 0 plus minus g alpha beta x tau x prime beta. So later we will take advantage of such a periodicity, meaning there's some sort of a periodic structure of this Green's function. Namely, I can simply just relate the Green's function between 0 and tau prime to the Green's function between beta and tau prime. So if you simply just draw a timeline, imaginary timeline, so this Green's function that's 0 and tau prime, so 0 is here and tau prime is here. So the Green's function between these two imaginary times, 0 and tau prime, is related to the Green's function between beta and tau prime. So this relation is telling you this. So there is some periodic structure of the Green's function telling you that you could simply shift your initial imaginary time from 0 to beta, and then you could calculate the other Green's function, but the other Green's function is related to the original one by a plus minus sign. And this turns out to be a foundation to actually derive the even odd Matsubarra frequencies for boson and fermions. So let me just summarize this periodicity of this Green's function. So the single particle Green's function, temperature Green's function, is actually periodic or anti-periodic, meaning periodic for plus sign for bosons and anti-periodic minus sign for fermions in the interval of 0 and beta. So let me just comment on this periodicity of this Green's function. So the upper sign plus refers to the relation for bosons. For bosonic Green's functions, you follow the plus sign, meaning you have a periodic structure of this Green's function between two different endpoints. But this minus sign refers to the fermions, meaning for fermionic Green's functions, if you shift your one of this imaginary time from 0 to beta, and you should remember the actual minus sign, because this is minus of the original Green's function. So because of the minus sign, we call this anti-periodic, and because of this plus sign, we call this periodic. So we will take advantage of such a periodic and anti-periodic boundary conditions for the Green's function at different time intervals, and we will derive the corresponding frequencies for bosons and for fermions. And for bosons, they are called even Matsubarra frequencies. For fermions, we call this odd Matsubarra frequencies. So this is the magic of this imaginary time Green's function and the consequence of such periodic, anti-periodic boundary conditions. So in just a moment, we will talk about this consequence of such periodic, anti-periodic bounding conditions for the Green's functions. Okay, so let's take a short break. So I suppose that these are a little bit technical involved. You need to convince yourself by moving around all these operators inside the trace, and then finally you convince yourself that this is the correct relation. So it's highly non-trivial, but it's not impossible to understand. So let's just make a final remark regarding this relations, periodic, antiperiodic boundary conditions for the Green's functions. So in most cases, we are talking about this system with time translation invariance, meaning this Green's function is a function of only the difference between these two times, tau minus tau prime. And the previous relation that we just derived tells us that this g alpha beta is a function of tau minus tau prime. When tau minus tau prime is less than 0, is negative, is related to the new time, which is positive because tau minus tau prime plus beta is positive, and with a plus minus prefactor here. So these two Green's functions are defined in the two different time domains. One is negative time, another is positive time. And they differ by beta. Remember, both tau and tau prime are within this range of between 0 and beta. So if tau is less than tau prime, so this time is negative, but then this Green's function defined the negative time is related to the Green's function with the positive time shifted by beta and with a plus minus factor. So for bosons, this tells us that this propagator or the Green's function of the bosons, function of time, imaginary time, has this plus 1 relations to d at a different time shifted by beta, tau plus beta. So which means that this is symmetric or even in tau. Remember, when tau is negative, and you could simply just shift this time to the positive, the other side of this time axis, and you still get the same correlation. But for fermions, you need to take the extra minus sign here. So we can use this relation to check the fermion of both vectors. The Fermi-Dirac and Bose-Einstein distribution functions could be derived from this periodic or antiperiodic boundary conditions. So we will come back to this later. But this is a very important lesson telling us that the mathematical structure of the Green's function in imaginary time domain really gives you the correct statistics of bosons and fermions, because the periodic boundary conditions of this for bosons will lead to this plus sign of this occupation, and for fermions, this leads to the minus sign down there. So if you solve for n cave 0 from both sides, you get, the Fermi-Dirac. I should say boson should be minus, fermion should be plus, right? So if you have such a relations, so this is nothing but the Green's function at two different ending time. So one is at negative tau, another is at positive tau by shifting the amount of beta, and then anyway, we'll get back to this relation later. So let's just look at this Fourier decomposition and multiple frequencies. So remember, the Green's function is periodic or antiperiodic between 0 and beta, but if I double this interval so that this time, tau and tau prime, are between minus beta and plus beta, and both Green's functions are periodic because you get double the period and minus times minus actually plus. So the bosons doesn't change sign. The fermion changed, minus 1 twice, so you get back to plus 1. So, between this minus beta and beta, the Green's function is always periodic. As a result, we could use this Fourier theorem to actually expand or transform this Green's function from imaginary time to this so-called Matsubarra frequency. So the Matsubarra frequency is something artificial because it is not a real frequency. You'll see later, because this comes as a conjugate variables to this imaginary time. So you can consider this as imaginary frequency. Okay, so-called Matsubarra frequency. So you'll see later that Matsubarra frequency is related to the real frequency by analytical continuation, which is a common trick in complex analysis. So we will talk about that analytic continuation in just a moment. But imagine this is just some function of x and tau, and we know very well that Fourier theorem tells us that you could decompose any function in terms of a complete set of eigenstates, or if this is a periodic within this interval, then you could simply just use this Fourier decomposition theorem to decompose this or transform this, this function g x tau the function x, g x omega, with this Fourier factor e to the minus I omega n tau. So here, this omega n is actually n pi over beta, where n goes to 1, 0, 1, 2, 3, and so on and so forth. So we will derive this explicitly, the values of omega n, in just a second. But you'll see that this omega n takes integer multiple pi over beta in this Fourier decomposition. So let's just invert the Fourier decomposition. Let's go backwards. So if we inverse Fourier transform this Green's function from g omega, from g tau to g omega, so this g omega n is given by this Fourier integral, which is given by 1/2 of this integral from 0 to beta plus another half from minus beta to 0. So you can simply just decompose this Fourier sum or Fourier integral into positive d tau or negative d tau, and you simply just add them too. So the first term is still the same, but the second term, you could actually use this periodic or antiperiodic bounding conditions to shift your tau by beta. And then you should carry a plus minus factor in front. The second integral, second half of the integral, reads the following. So let me just repeat this derivation one more time. So this is the definition of this Fourier integral between minus beta and beta of this Fourier sum. But you could decompose this in terms of the positive time integral and negative time integral. And for the positive time, you simply just copy this. You don't do anything. But for the negative time integral, you simply just use the periodic antiperiodic bounding condition for this Green's function, and you shift this tau by amount of beta. So tau becomes tau plus beta, but then you need to carry this plus minus sign. So the reason why we're doing this, because we would like to actually combine these two pieces of this Fourier sum together. So let's just try to combine these two. The first term is the same, but the second term, let's just shift origin or change the variables from minus beta 0 to 0 and beta. So in doing so, we simply just shift our tau by tau minus beta. So we simply just shift tau to tau minus beta, so that this upper and lower bound of the integral now changed to 0 to beta, and this tau is shifted to tau minus beta, and this g tau plus beta becomes g of tau. Sounds like magic. So now you are able to combine these two g of tau, but then you need to pay attention to the prefactor, because the prefactors are not exactly the same, right? So the first term carries the prefactor e to the I omega n tau. The second one is actually plus minus sign times this different exponents here. So let me just combine this for you. So this is 1/2 of 1 plus minus e to the minus I omega n beta 0 to beta d tau e to the I omega n tau g of tau. So as I mentioned already, this omega n in this discrete Fourier sum takes the value of the integer multiple of pi divided by beta, because this is how you define this Fourier decomposition. And this Mossbauer frequency takes the value of this integer multiple pi divided by beta that come from the definition of the Fourier sum. And you simply just plug in this definition of this omega n here. So you'll find that this factor, so let me write here, this factor minus 1 to the power of n here, which is 1. So we need to separate these two cases. First the plus sign, and second minus sign. So the plus sign, so this factor gives you 1 when n is what? Even. When n is even. If n is odd, then this 1 plus minus 1 to the power of odd power, which is minus 1, so 1 minus 1, 0, it vanishes. So it gives you finite value only when n is even. And this is so-called bosonic Mossbauer frequency. And for the minus sign here, it is opposite. So when it becomes odd, you get a 1 minus times minus 1 to the power of odd power, which is minus 1. So minus minus plus, so it gives you half of 1 plus 1, which is, and this is so-called the fermionic multiple frequencies. So we immediately get a very important conclusion here. So when we Fourier transform the Green's function from the imaginary time to the multiple frequencies, there are two different kinds of multiple frequencies. One is bosonic, another is fermionic. For bosonic, you get 2m pi divided by beta. For fermionic, you get 2m plus 1 pi over beta. So later, we will understand the relation between this bosonic and fermionic multiple frequencies and their statistics. Namely, for bosons, because the multiple frequencies are even integer multiple pi over beta, so it leads to the Bose-Einstein distribution. And for fermions, because this is odd integer multiple pi over beta, it leads to Fermi-Dirac. So there is a one-to-one correspondence between this even odd nature of the multiple frequencies and their statistics for bosons and fermions. So I think that's a good timing to take a break, and I encourage you to read the corresponding chapters in Flansburg and also in Effective Logica, also the other references where you can find all these identities in their books. So this is a very important part of this many-body Green's function, especially at finite temperature. So you have this very elegant way to derive the Fermi-Dirac and Bose-Einstein distribution functions simply based on this multiple frequencies and periodic, anti-periodic nature of the Green's functions. Okay, so let's take a short break. So all these tricks that I played here is just some kind of a mathematical treatment of complex functions. And we need to find a way out to really help us to make progress. And this is the only way that we can make progress. So after this multiple frequencies are introduced, we will go back to this real-time Green's function and trying to define all these physical observables of the real-time Green's functions and their Fourier transform. But then we end up with some troubles, as I mentioned already. So without going to this imaginary time, it is impossible to really calculate this Green's function. So we need to take a detour first to go to the complex plane, imaginary time axis, and then we are able to calculate this Green's function in the imaginary time domain. And we make a Fourier decomposition, taking us to this multiple frequency axis, and then we will take a detour back to the real-time domain by analytic continuation. And so we will talk about this analytic continuation later, and after this, I guess you will realize that and appreciate what we are doing here. So let me just sketch So this is sort of a detour that we are taking. So the Green's function in x and t, variables are the target quantity that we want to calculate. Okay, so especially when we Fourier transform this capital G xt to capital G k omega. However, as I mentioned, at finite temperature, it is not possible to really go from here to here. As I mentioned, the thermal factor cannot be simplified and combined with the time evolution because they are not the same kind. Okay, so we need to take a detour. The detour takes us from capital G xt to italic G x tau, where tau is actually defined as I times t as imaginary time. So then, we can do something about that because we know how to combine all this thermal factor and the imaginary time evolution operator. Okay? And then we can Fourier transform this italic g x tau to italic g k omega n, where omega n is a Matsubarra frequency. Okay? So, however, this is not the final step because we need to go back to the Earth, right? We take a detour to the outer space, but then we need to go back to the Earth. So the way that we go back to the Earth is to take the analytic continuation by identifying this I times omega n, where omega n is an imaginary frequencies, right? As the real frequency omega plus or minus some small imaginary part, which we'll discuss later. So this function, italic k Matsubarra frequency, is actually reduced to this capital GK omega if we identify this I omega n as the real frequency plus a small imaginary part. So as a result, we are able to really compute what we plan to do. So we go for a detour from here to here, and finally we arrive here. Okay? But if we go directly from this capital to capital, it's a dead end. So there's an old saying that the shortest distance between 2 points is not a straight line. Sometimes the detour path is the shortest distance. It's the only way that we can get to our endpoint. Right? So you understand this philosophy now. So what we are calculating is something artificial, but this artificial function is actually reduced to real observables once we make such identifications. Okay? And this identification is actually justified in this complex analysis. It is nothing but so-called analytic continuation. So we will introduce this idea later on, but this is already in your applied math that we could analytically continue a complex functions to the real axis or imaginary axis. So let's just look at this very simple examples of non-interacting Green's functions. Of course, at finite temperature. So let me just write down these formulations. You could check your references and textbooks. So anyway, we will come back to this later. So when we talk about the non-interacting Green's functions. So here I simply just summarize the result. So this is a general formulation for this non-interacting Green's function finite temperature. So this phi j0 x and phi j0 x prime refers to the single particle, say, creation and destruction operator, and also the corresponding wave functions of the single particle. And energy denominator comes from this, this d tau integral. And you will find that this factor 1 plus this occupation number, nj0, will get exactly cancelled if you carry out this integral. Exactly. So for fermions, we get this, and for bosons, we get this. So anyway, we will come back to this when we get there. So this is just a summary of this non-interacting Green's function at finite temperature. In other words, we are able to derive the non-interacting Green's function for fermions bosons based on this Matsubarra sum. So let's just come back to this temperature Green's function in real time and the linear response that we talked about in the very beginning. So let's just look at this, again, single particle Green's function, but in the real time. So again, this is our target quantity, right? Right here. So, of course, we could formulate this real-time Green's function, the finite temperature. It's just that we don't know how to calculate this. Okay, it doesn't prevent us from formulating this. It's defined like this. So because this is real time, so there's a factor of I here in the definition. And this bracket here refers to the thermal averaging. And this K is again Hamiltonian subtracted by the mu times number of particles. So, we restrict ourselves to the time translational invariant so that this Green's function is a function of only the difference between these two coordinates. And we also restrict ourselves to this spatial translational invariant system so that this Green's function is only a function of x minus x prime. So that we could simply just shift one of this coordinate x and t to 0, 0, and then discuss this, this correlation in only x and t. Okay, so this is just some definition, and let's take a short break. When we come back, we will start to analyze the spectral representation of this real-time thermal Green's function. So let's continue. So this psi k alpha xt is the destruction operator in the Heisenberg picture. So by definition, this is given by the Schrödinger operator, sandwiched in between this e to the ikt and e to the minus ikt operator. But this k refers to this Hamiltonian operator subtracted by this mu times n. So then we restrict ourselves to the translational invariant system where this momentum operator actually commutes with the Hamiltonian. So in this case, we can actually use the plane wave e to the ipx as the basis to express the single particle operator. So you can show that this commutator between this destruction operator, psi alpha x and p, is actually minus delta I gradient psi of alpha, whereas momentum vector is actually defined as this operation following quantum mechanics. So it is easy to show that you could simply just solve this or express this psi alpha x in terms of this e to the ipx, e to the minus ipx operator. So in other words, this momentum operator actually generates this translation in your system, and your single particle operator can be expressed in terms of this eigenbasis of this momentum operator. So this looks like the same as this in the time domain, right? So this is the Heisenberg operator. This psi xt is given by this unitary transformation, and in a similar way, in the translation invariant system, this single particle operator psi of x is given by psi x equals 0, sandwiched by this kind of a plane wave eigenstates or eigenfunctions of momentum operator. As a result, you could simply just combine these two, and you can write the Heisenberg operator for a single particle, destruction operator is given by this double unitary transformations, and you start with the destruction operator at x equals 0, t equals 0, and then you simply just transform this to x equals 0 and time equals t, and then you make another unitary transformation, takes you from x equals 0 to x equals x. And this is true only when this momentum operator actually commutes with the Hamiltonian. Okay, because then as k is Hamiltonian operator, it's actually commute with the momentum, so that you could perform such a double unitary transformation. So we can plug in this kind of double unitary transformations of a single particle destruction operator into the definition of the Green's function. And this is what? This is psi alpha xt, and this is psi dagger beta of 0. Because we already shift one of the coordinate x and t to 0. So then by definition, at finite temperature, this is given by this partition function, the denominator, times the trace of this stuff. Right? So since we already mentioned that the momentum operator is actually commute with the Hamiltonian, so in other words, we have a simultaneous eigenstates of a momentum operator and the Hamiltonian operator k, okay? Because p commute with h minus mu n. So we can find the simultaneous eigenstate of the momentum operator and Hamiltonian operator k. So we could, expand this trace in terms of any arbitrary complete set of eigenbases, right? So, but in this case, since p commutes with k, and the obvious natural candidate for this basis is the simultaneous eigenstate n. So we can expand this, trace of this complicated operator product in terms of the simultaneous eigenstates of momentum and Hamiltonian operator. So let's do it. So if t is positive, then we get a g greater function, and you simply just insert this complete set of eigenbases. So I insert this complete set of eigenbases here and there, right? Following quantum mechanics, I can insert any unit, operator I want, and this unit operator is made of this complete set of eigenbases n with a Dirac notation, right? So I simply just use this and I plug in this to this trace, and this is what I get. And I can simply simplify this. So let me just finish this. So this is the final expression. Once I insert this complete set of eigenbases inside this trace, and I get this expansion, right? And because this matrix element is actually the complex conjugate of this matrix element, as a result, when you take a multiplication of this matrix element, you get the square of this matrix element. This will serve as the basis to analyze the spectral representation of the Green's function at finite temperature in real-time representation. Okay? So in other words, we could expand this single particle Green's function at finite temperature in real time in terms of this simultaneous eigenbasis of momentum and Hamiltonian operator. And then when we finish, we get this complicated matrix element square times this exponential factor of this time evolution and spatial translation, and also the thermal factor. Okay, so again, this is just a formulation, and it doesn't mean that we are able to calculate the things. As I mentioned, we are not able to calculate the things because, again, we cannot combine the thermal factor with the time evolution. But still, formally, we could write down such a spectral representation of Green's function, and then later, with the help of the imaginary time Green's function, we can link the imaginary time Green's function to the real-time Green's function, like this. Of course, this is the physical observable, right? So anything that could be measured in the lab is related to this function, not the imaginary time or Matsubara Green's function. But this one, this is real. However, we cannot do anything about this. So it's there, but it's useless. However, with the help of this imaginary time and Matsubara Green's function, we are able to access and link what we calculated to the real world. Okay, so this is the real world, but we cannot access at this point. So let's take a short break. We'll come back, just continue with the spectral representation of the single particle Green's function at finite temperature. Okay, so for negative t, we could follow the same logic and calculate G lesser Green's function. But remember, we need to pay attention to this plus minus sign, because now when we calculate G lesser, we need to switch the order between psi and psi dagger. And when we do so, we need to pay attention to this, whether this particle is boson or fermions, and for bosons plus and for fermions minus. And we can show that this is given by almost the same expression as that for t positive, except we have this plus minus sign. So we can combine these two parts of this Green's function and to get the total Green's function. And we can decompose this into G greater and G lesser Green's function, right? And so we can Fourier transform this to gk omega. Of course, this is what we want, but this is another easy step because we need a detour. Okay, but ideally, once we have this g bar xt, which is this, and by a Fourier transformation, we are able to get the gk omega. And you simply just plug in this g lesser and g greater as functions of x and t, and you could show this gk omega is given by this. And we need to introduce the convergence factor, a small imaginary part I eta, where eta goes to 0 plus, for the same reason that we introduced the small imaginary part earlier when we talk about this zero temperature Green's function. So in order to get the convergent results of this Fourier transform, we need to introduce a small imaginary part I eta, plus I eta for this g greater, and minus I eta for the g lesser, and pay attention to this plus minus sign here. So with this at hand, we are able to integrate over this time domain and get this g as function of k omega. Remember, this is a generalization of the single particle Green's function zero temperature, but now it is at finite temperature, so you get a thermal factor here. So it's much more complicated than the zero temperature Green's function. So let's just do it, and you could show that there is a momentum conservation factor and matrix element square, but most important part is this thermal factor here. Okay, so you can very safely integrate over this dt here to get an energy denominator. But then you need to pay attention to this plus and minus I eta. As I mentioned, if you do not insert such a factor, you'll get trouble. What kind of trouble? Well, you can immediately see this trouble, right? So for this positive time, you get 0 to infinity dt e to the minus eta t, right? This factor. So when eta is small positive value, and this convergent factor guarantee that this integral will not diverge. So in the second term, you get minus infinity to 0 of dt e to the plus eta t. Remember now this time is negative, so again this is a convergence factor to guarantee that this integral does not go crazy. Okay, and as a result you get this plus I eta and minus I eta in its two terms after you integrate over dt. Okay, so this is the general formulation of the single particle Green's function at finite temperature in many-body background. And we will analyze the pole structures and the thermal factors next time. So you immediately see that this is more complicated than this zero temperature Green's function in the sense that you have a simple pole at omega equals this value. Okay, but then the residue is somewhat non-trivial because this residue has this complicated structure that this is a square of the matrix element, but then you get two different kind of the thermal factors. And everything will be linked to this, again, Fermi-Dirac or Bose-Einstein distribution function, and we will make such link next time. And this is the thing that we could measure in the lab. And you can take the real and imaginary part of the GK omega at finite temperature, and this is it. But again, the question is we cannot do anything about this unless we can really make progress in the imaginary Green's function. So let me finish this by saying this residue, matrix element square, vanishes unless nm is actually nm plus 1. So we will explain this condition next time. Right? So this residue is actually matrix element square, but as I mentioned, this is the destruction operator. So the number of particle in the state n should be one more than this particle in the state n, because this is the only way that you can make a non-zero matrix element, because you destroy a particle in the n plus 1 system, and you go back to the n particle system, which is the same as the Dirac-Brock state, and as a result, these two states sandwich this destruction operator gives you a finite value. If you don't get the same particle number between Brock and Cat state by orthonormal conditions, you get 0. Okay, so this tells us that we could use so-called Lehmann representation or spectral representation of the Green's function in K omega space by analyzing the excitations of this n particle system, either by increasing the particle number by 1 or by decreasing the particle number by 1. And those energy difference corresponds to the excitation energy of your n particle system, because now this energy difference is between n particle and plus 1 particle system. So let's just end our lecture today right here. So let me summarize. So we studied this periodic structure of the Green's function, and we derived the Mossbauer frequency for boson fermions, and we start to define this temperature Green's function in real-time domain. And the next job is to link everything together. So this real-time, or capital GK omega, should be related to this italic G K I omega n, where omega n is the Mossbauer frequency. So next time, we will make such a link between the real observable and this so-called imaginary Green's function. So I guess that's it for today, and I encourage you to read the corresponding chapters and sections in our references books and get familiarized with all this Green's function different domains. And later you will find that this is very useful to analyze all the things that you are familiar with in elementary introductory level of the solid state physics. So see you on next Monday then.